introduce myself. Yes, team. My name is Abhinam, and I'm working as a PD engineer in one of the service is VLSI company.
Yes, it's visible.
It's visible. Okay. Now,
Yes, we can see that.
fundamental concepts in physical design, right?
Yes, we can see.
Okay. Okay. I'm sorry, guys. I'm sorry. Actually, even I also like we are very good at Zoom sessions and all. Sorry. Fine. Now, guys, see here. Whatever we discussed about the introductory slide, the physical design comes under back end, and we discuss, guys, in ASIC design cycle, what are front end areas and what are back end areas, and when the design idea when it becomes as an IC, like what are the internal stages and all that comes under ASIC design cycle. We will see soon. And goals of physical design like PPA or ATP, and we deal with standard cells only. Now, I hope we can go to the next slide. Yeah, you see, guys. See here, technology. It is the distance between the source and drain. That itself is the technology, or you can consider it as a gate length as well. So the new technology is always equal to 0.7 into volt technology, because according to Moore's law, the number of devices fitted into a particular core area might becomes double for every 2 years. Becomes double in the sense the area is getting reduced to half in the sense 0.5. So where we have the three-dimensional view, x-axis, y-axis, z-axis, where z-axis is thickness, it is fixed almost for a given technology. So here it is x into y. If I take 0.7, 0.7 into 0.7, we get almost 0.49, which is 0.5. So for one axis, as it is 0.7, the new technology is 0.7 into old technology. So that's what here you can see here clearly. For every generation, we integrate double the number of elements per chip. And yes, team, remember, the latest technology has highest frequency of operation. Remember, of course, the latest technology, whatever, the fab cost, I mean to say the fabrication cost is a little high because the yield is very less, guys. You can ask me what is yield. That I can say the number of good chips. Just a second. Or else, yeah, the number of good chips is equal, like the number of good chips by the total number of chips into 100. So because of the latest like technology has high frequency of operation, the number of good chips coming out of the process are less. Hence, the yield value is less in latest technology. Because of that reason, yes, the lower technologies fabrication cost is very high, guys. Remember. Now, let's enter into ASIC design cycle. Yes, guys. See, this is the ASIC design cycle where it includes specifications, design verification, synthesis, place and route, static timing analysis, physical verification, fabrication, packaging. Guys, from stage number 4 to stage number 7, like synthesis, place and route, timing analysis, and physical verification comes under back-end design, and stage number 1, stage number 2, stage number 3 comes under uh, front end. And once after completion of physical verification, we have to manufacture the IC, and that comes under fabrication and packaging. Once that is done, I mean packaging is also done, team, we can say the IC is ready. Now we have the IC physically. But you know, once the IC is ready, you need to check it out whether it is working as per your design functionality or as per your design, the speed as well. Team, remember, while manufacturing the IC, not only the functionality, the time is also important to us. Because let's assume it is a 4-bit adder and you have given 4 bits, A and B whose length is 4 bits, and you are getting the sum after 10 years. Yes, it is giving the answer without any error, but still, please wait for 4 more years. Means you cannot do in that way. You want the functionality within the desired time. So for us, the functionality and the speed, the time period is also important. So here, even here I have included the major stages, and even in backend also there are some few more intermediate stages. Okay, but here I'm highlighting the main stages. Now let's enter into ASIC design cycle. Yeah, specifications, guys. In this stage, remember the outcome is a Word document. Means it includes like either functionality or performance. Means especially here, what are the inputs required, what are the outputs required, and its functionality. Here, if you ask me who is going to finalize the specifications, and these specifications might finalize with the customer and the design engineer. The customer will give you or the client will give you the design idea or the market need. Like in this market, I want to introduce this product. So for this product, these are my inputs and these are my outputs. So both the design engineer, maybe the top level guy who is very senior, might sit with the client and he will finalize all the requirements for for the design. And as I said earlier, for the specification, in the specification stage, the outcome is a just Word document which contains inputs and outputs. And even, of course, it follows the functionality as well. Now, guys, after the specifications, we will go to the design time. It is also called as RTL design, where RTL refers register transfer level design. And in this stage, guys, whatever the functionality they have they have forwarded, they have proceed for that functionality, we write the code in any one of the hardware description languages. Here HDL refers hardware description language. Either it could be VHDL or Verilog. So most of the design engineers prefer Verilog as it has more facilities or provisions compared with VHDL. So it is not mandatory saying that you have to go for only with Verilog. You can go with either VHDL or Verilog. Okay. So in this design stage, RTL team takes a Word document and they implement the code as per the functionality. Yes. Remember team, if you ask me, sir, these RTL team with respect to the technology, no. RTL team works independent of the technology. They don't bothered about the technology. Simply they must they may concentrate on the code. That's it. Let's have one half adder very log code team. You can see right side of the slide, module half underscore adder ABSC, where AB comes under inputs. SC, sum and carry, belongs to outputs. Input A comma B, output S comma C. And hope you know for the half adder, for the sum, we use XOR gate. So that XOR S comma A comma B. And for carry, we use AND gate. So AND of C comma A comma B end module. This is a simple code for half adder. Okay. And guys, remember, in this RTL verification, like RTL stage, we mainly concentrate on the functionality, which is the behavior, okay, rather than implementation, how they implemented and what are the interconnections and all. We don't see and we don't bother. We mainly focus on the functionality. That's it. And in this stage, if you ask me the outcome, what is the outcome? It's simply an RTL code for your specified design functionality. That's it. Now, guys, the next stage is verification. The RTL team have written the code and they have sent it to the next stage called design team, or mostly people say DV, design verification. What is the job of the design verification team? They take the the RTL code and they give some set of inputs, and they'll check whether the output is as per the functionality or not. Let's assume half adder only. Coming to the half adder, you know, it is a 2-bit adder. The two bits could be 00 or 01 or 10 or 11. It could be any one of the combination. So they give all the combinations either 0001 1011, and they'll check the outputs accordingly. I'm not saying if the inputs are 1000, then the combinations will be 2 power 1000, isn't it? So if there are two inputs, the combinations are 0001 1011. In the same way, if a design has more number of inputs, say for example 256 inputs, then the combinations could be 2 power 256. So remember team, design verification team, uh, whatever I mean to say, the job is not that much easy. So it's simply giving the inputs and getting the outputs. No, there are different strategies they need to follow to check the functionality for almost all combinations. So here at verification stage, we want to see the richness of the RTL code. Means whether the RTL code that written has been written, is it a a good good to go signal? Is it all good to go signal? That we need to verify. So that's all we do it at verification stage. And remember team, you can ask me, sir, suppose RTL code has some fixes, some updates, then design verification can change the code. No, even though you people are aware of RTL, like RTL job, you are not supposed to do. Simply, you need to inform to your lead or manager saying that there might be a bug. There might be like for few cases the it is not working as specified, so that those people will inform to the RTL team. So you don't have the involvement in manipulating the code to work as per the specifications. So remember that team, guys. Okay, and let's go to like see guys, till RTL and design verification, that comes under front end, that is independent of technology. So they don't bother about on which technology they are working. No need at all. Of course, remember team, if you ask me, sir, the people who are seated together and in stage one specifications, you said one design engineer and the client sit together and they have written everything, they have finalized everything. At that time, that might finalize it, the technology and the what is the package and all, the fabrication technology and all. Yes, but coming to the RTL team, they don't bothered about the technology. Remember that. I hope you got that point. So they might decide it, but coming to the RTL team, they don't know about the technology. That like both RTL team and design verification team. Now let's see synthesis team. Till now, we are saying that physical design concepts, fundamentals like that. I hope some of you like might from physical design. like maybe most of the you people, it is physical design. In physical design, there are three very important stages. I'm not saying only three, but majorly there are three important stages. They are synthesis, place and route, and static timing analysis, STA. Now, let's see the first one, synthesis. Team, just now we have discussed about RTL and design verification team. They have given us the RTL code only as per the functionality. Of course, it is functionally it is correct. Now, what is the job of synthesis? The job, like the synthesis job, is simply preparing the optimized gate level netlist for meeting the area and timing power for the targeted technology. So we want to convert the RTL code into gate level netlist. We will see one by one what is meant by gate level netlist, what it contains and all. Team here, the synthesis team will take the RTL code and they implement. For example, till now I said for the RTL code, you see here XR and. But what is what we call the internal structure, internal connections from the A and B inputs, how you are taking the XR gate inputs. For example, if it is a full adder, it may require three AND gates to produce the carry, how they are interconnected. The actual implementation happens in synthesis. So here at synthesis, we take the RTL code and we implement for that particular RTL code. And of course, not only implementation, just sir, is it a converter from code to implementation? No, not only a conversion, there is optimization as well, so that you can meet your constraints. Our constraints or our goals are simply area, timing, power, guys. Remember, okay? And moreover, guys, here, as I told you, while implementing, we keep on tracking with respect to the parameters called performance, area, and the power dissipation. Now, coming to the synthesis, and especially guys, I want to tell you one thing. Some of the people, not most of the people, and I am not saying that that is their disadvantage or whatever. That is the lack of unawareness. What they think is, in VLSI we use only one tool. No, in different stages we use different tools. For example, you take synthesis. For synthesis, to convert this RTL code into optimized gate level netlist, we use genus tool in cadence environment or design compiler tool in synopsis environment. The major tool vendors are cadence, synopsis, and of course two more are there, few more, but mainly we take like either cadence or synopsis. And team, remember the tools which we are using at this stage only, because as I said, I am assuming you don't know anything regarding the VLSI physical design. So we are cultivating the subject from the roots of the subject. So like cadence and synopsis, the tools which we are using are important. So as I said before, team, remember, from synthesis onwards, it is all technology dependent. And at synthesis, you come to know on which technology you are going to work. If you ask your lead, he might give you the information on which technology you are going to work. Okay. So one bottom line about synthesis. Synthesis simply converts the RTL code into optimized gate level netlist. The gate level netlist contains the actual implementation of the RTL code with its interconnections. That's it. In an optimized way. It is not simply gate level netlist. It is an optimized gate level netlist. Once synthesis is done, we come to know these are the modules you require, some 10 adders you require, and 10 D flip-flops you require. and some 10 transmission gates you require. Like that, you come to know. Yes, in synthesis, from the standard cell libraries, we get the cells and we make the interconnections. Of course, remember, team, in synthesis, the wire delays are zeros. When you take any a design, it contains two types of delays: cell delay, wire delay. Cell delay, the delay, the time taken by the cell or by the device to show the output whenever there is a change in the input. That is what cell delay. However, the net or the wire or the interconnection also has some distributed resistance and capacitances. These resistance and capacitances introduces some delay definitely, and that delay can be considered as wire delay. So the total delay can be the sum of cell delay and wire delay. Now, in this case, at synthesis, remember team, wire delays are zero. By default, we consider wire delays are zero. However, there is a provision. You can fix to a particular value. Let's assume you can fix that particular wire delay as some fixed value, some 10 or 20 or 30. It could be some auto wire load model or some customized zero, like customized wire load model that we will see in synthesis. At synthesis, you will understand what is meant by wire load model, what is their impact, what is a percentage, and all we will see. But as of now, at synthesis by default, we are assuming wire delays are zero only. Now, coming to the place and route. Team here, as I said, in place and route, as per the functionality, I mean, as per the modules that we come to know at synthesis, we want to place them in our core area. Yes, we need to place them. How can you place? Where you place? In place and route stage, we do it. So if you ask me what is meant by place and route or PNR simply, at PNR stage, the input, the main input is netlist. Of course, we have few more input files required at PNR, but the main thing from this like a synthesis is optimized netlist, and we take this netlist and we map in such a way that we get the physical layout of that particular ASIC design. So here this place and route contains some of the stages, like whatever the core area. First you need to plan the core area where you need to place the standard cells. We have so many standard cells. Let's assume PLL, phase locked loop, to generate the clock, and you require some sequential cells like flip flops, or you require some adders, or you require some some other modules like memories and all. So before that, team, let me tell you, in a fast span, for example, one person purchased the land and he wants to construct a house. Suppose, let's assume it is a east facing. So as per the vastu, it's a good to go signal from the east. So whenever he wants to enter from outside to the house, most of the times we may take it as a hall. We don't place washroom at the beginning. Yes, obviously we take as per the vastu or with a few more relaxations at somewhere else in the particular place, but not immediately entering into the home. Or where you need to place the puja room, where you need to place what we call the washing area or bedrooms and all. We have a particular plan. In the same way, you need to plan the floor, the entire core area, according to the specifications or requirements, and that is called floor planning guidelines. At PNR, there are some set of floor planning guidelines in such a way that where you can place all these standard cells or the bigger cells more than standard cell. We usually call it as macro. Macro is a bigger standard cell where you don't have the right to enter into the functionality. You can connect to the inputs and you can get the outputs. We have only access at inputs and outputs. That is called macro, a bigger standard cell. So where you can place, how you can place and all, you need to do it as per the floor planning guidelines. Remember team, in our VLSI, the tools are so matured. The tool will give you all the suggestions and directions to you. But in our PNR, the one of the crucial thing is floor planning. You need to place the like the cells. I mean, what we call the macros, the bigger standard cells manually. Of course, some percentage there might be on automatic, but some of the macros that you need to place manually. This is one of the challenging job for a PNR engineer. So most of the times the tool will take it, like will take care, but placing the macros is your job as a PNR engineer. Remember. Now you see at placement and route, we place the stand make macros and standard cells, and we see the route also. Team, remember the terminology is very important. That is, like you can call this ROUTE as route also, but please don't call them as a route. It is a route only. So the terminology which you are using at industry is very important. So you like I suggest you use the correct terminology. Like usually at our BTech studies, people say in order to overcome this, in order to overcome this disadvantage, like that. But at industry, the people use the word like we want to fix it. How you fix it? I want to fix it at any cost. People say like that. So don't get confused. In order to fix it, or I want to fix it, it is simply they want to remove that whatever the disadvantage or whatever. So that's what. Just it's an example. Maybe you might have more than like these terminologies and all, like about the words which we want to use at industry. Now let's move on. Team here in placement and routing. One of the very important stage is placing the macros, which is called floor planning. As per the guidelines, we place the macro cells and all. And here, uh, the tools we use at PNR stage is Innovus from Cadence and the IC compiler, integrated circuit compiler 2 in Synopsys environment. Guys, here most of the times either you can go with either Cadence environment or Synopsys environment. But nowadays, like at industry, most of the people may prefer Synopsys, maybe because of the flexibilities or because of the like the facilities or provisions made by the Synopsys. But most of the times we prefer Synopsys. But uh, at training means when you are at the initial stage, it's better to learn through Cadence, because through Cadence it gives you more what we call uh, like more details, design details. Hence, most of the training centers may prefer Cadence as even as well as Synopsys as well. Now, guys, after place and route, we go to static timing analysis. Team, remember, at synthesis we check the timing, so don't forget that. It is not like only at a static timing analysis STA we are checking the timing. At synthesis we check the time. At PNR we check the time. However, whatever they provide the information regarding the timing may not be the final one, because There are doctors like general surgeon for fever or for any some minute or even some medium level disease also we go to the doctor and he specify whatever the like medicines or course we follow. But whenever the disease like the percentage is very high, that means he has a very severe chest pain. People say, why don't you go to specialist? You can go to the heart specialist, or you can go to the kidney specialist, or you can go to the ophthalmologist, eye specialist. In the same way, static timing analysis is especially designed for the timing. Even though it's synthesis and PNR, we check the timing, that is not final. Whatever they give the results are what we call the conclusions are fine, but they are not final. Whatever the STA team people gives the results or conclusions, they are the final judgment for our flow. Remember team. So in STA, we don't bother about the functionality. Remember guys, if you ask me sir at STA, do we bother about the functionality? No. We consider exactly speaking the timing. Whether is it providing the output at our design, the desired time of span, is it yes? That we are going to check. That's it. So here uh, we use Tempest tool for cadence environment and prime time in synapses environment. As my friends who are along with me in um, industry, and they said the prime time tool works better compared with cadence. Yes, we need to agree. Actually, I'm working in PNR team. Okay, so here like whatever the inputs I got from my from my colleagues and all, like they say they mostly prefer prime time for STA. Yes. Now guys, once that STA is done, we might go to fabrication. Yes. Coming to the fabrication team, we get the post layout information from PNR. Yes. And yes, it's a timing clean. It is working as per the desired time. Then we need to fabricate it. First of all, what are the fabrication plants? Or in a technical way, you can call them as foundries. They are TSMC, UMC, and Global Foundries and SMIC. Here, these are the foundries who fabricate the ICs. You might see during Corona, guys, more like the doctors might wear the blue color, sorry, the white color jacket with goggles. Everything is closed to protect to protect themselves from the virus. The same dresses the people wear in VLSI since ages, means from 19 19,000 like 1900s areas. From there only people use these specialized dresses or specialized uniforms during the fabrication, because that's very very sensitive. If something goes wrong, if a very very small dust particle enters, then also your entire core area is going to vanish. Entire the process is going to vanish, and you need to start from the from the basics or from the roots. Hence, we need to take care like a very high, extensive, rigorous care, especially during the manufacturing. And that fabrication includes various stages like ion implantation, oxidation, photolithography, or etching, or wafer preparation. At VLSI analog layouts, like you might come across even in VLSI in your BTech studies, some Jokralski process. In that Jokralski process, there will be some cylindrical furnace where it is moving in a particular clockwise direction, which contains a pure silicon, and they take one silicate seed and they'll dump into the particular pure silicon liquid. I mean, in that one, and by using that Jokralski method, I mean to say, the furnace is moving in a clockwise direction, and that seed, whatever the spindle, is moving in an anti-clockwise direction, so that it forms one like a cylindrical shape, and then later that they cut it into slices, and they'll take one which is called one slice, and again they'll cut it into horizontal and vertical pieces, and one of the piece is a wafer. That's it. So you get more about this one in analog layouts, and we are not much about like like this stage for our PNR. And now, guys, here, apart from the fabrication and all, like once the design is ready, we need to have the desired package also. Means packaging in the sense, here, just a second, here there is a YouTube short video. I'll show you so that you'll understand what's inside the IC. Just a second, team. Is my screen visible, team? Hello?
Yes, sir, visible.
Okay. Yeah, you see this, guys. Yeah. So, is my screen visible? Please, someone, please confirm.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yeah. So, team, till now, what we have seen is till now, after fabrication, that whatever that object is ready, but you need to protect from the environment, such kind of like corrosion or from the humidity, from the wetness and all. So for that, a proper package is required. You know, if an IC contains the metallic pins at two sides, that is called dual in line package, DIP. And you can take microprocessor 8085, 8086 are the examples, because you can see from right hand side, left hand side, you can find the pins. But you know, there are some ICs where the pins are present in all the four sides, and hopefully you know that it is a quad package. And even you can find the pins below the IC, they are called pin grid array. And you know, most like the funny thing, as the pins are consuming the power, some of the ICs are not bothered about the pins. Means we are getting the ICs without any pins, pinless ICs, because for them the power is very important criteria. low power design might be. Hence, guys, there they don't consider even pins as well. So for your particular IC, the package is also very important along with your all hardware. I mean goals like performance power area, PPA or ATP. The package is also important whenever it comes after the fabrication. Means after the everything is done. Now, team here, you can see before going to the next topic, here I want to tell you one more point. After completion of this, like after manufacturing the IC, there is one more stage that is called post silicon validation stage. What they're gonna do at post silicon stage? At post silicon stage, the engineers takes the IC and they check the functionality, means whether it are is the IC is working at as per the functionality and within the design time. Was it what is its power dissipation and all they'll check. And once that is done for various combinations at various stages at various temperatures, then only they'll recommend the IC to release into the market. Remember, team, that's what the reason, because the IC can be used in Kashmir where there is a minus degree centigrade, where they might use in some other Africa or some other areas where the temperature is very very high. The temper like the, even some like hope some of the countries have the day period very high. Usually, I hope most of the people are from India. Like we have a very good environment saying that some 7 to 8 hours of full day, and we have moon and we have darkness. We have a good atmosphere and all. But whereas in some continents and some areas, you get 6 months day and 6 months it is night, or maybe some 12 to 18 hours day and some 6 hours night and all. So the IC may work in any area, and you need to design that IC so that it can work at a any temperature specified in the levels, at any frequency specified, some power dissipation range. So here you need to check whether they are meeting the specified constraints or not. That is what the post silicon validation job, guys. Okay, here few more few more stages are there. For example, I said standard cells. We take the standard cells from the library during the placement. So some people might already already designed those modules, those standard cells. They are none other than analog layout people. Analog layout people takes the specifications and they manufacture, I mean they design that those standard cells and they will give it to us, of course, with respect to money transactions as well. Because guys, see, our journey is getting the post layout file after the PNR stage. In our journey, some of the modules you can get it from the outside. Yes, because preparing everything by you is not required. Some of the people have already designed that. Then why don't you take them? Again, taking that and starting from the seed and all may not be a good approach, because the timing, guys, the your competitor might come and he may go beyond your timing, and you are going to release the product by this December, and your competitor might release the same product in the month of August, so that all the customers may shift to his product, not your product. So there might be heavy competition. That is the reason when you allot to the client, except your team and except you people, no one has right to enter into your block, because that person might enter into your office premises and he took the schematics or all the design information, and he can beat you with respect to the time. Hence, that is very very sensitive and more secured as well. So the timing is very important, and you need to complete within the stipulated time. That's what all I mean, guys. So this is I can say ASIC design cycle team, the various important stages involved in this ASIC design cycle. Now, yeah, it is around 1 hour. Can we go 20 more minutes, team? Just a second, I'll confirm with Rajat.
Mm. Yes, we can do it. No problem. Just do it.
Okay, then. Okay, good, good. Yeah, team. Let's see the second topic, like delays, because as I said earlier, the timing is very very important to us. So for that, first after the design cycle, I want to discuss with you people the delay only. Yes, team, coming to A to Y, where A is my input, Y is my output. From A to Y, there are two types of delays are involved. One is gate 1 delay or cell delay. Next, net delay or wire delay or interconnect delay or metal wire delay. You can take any one of the word. And even there is one more gate, and that gate also. So at this design, the total delay involvement is the first gate cell delay plus net delay plus the second cell delay. That's it. So I can say there are two types of delay: cell delay, wire delay. Now let's talk about net delay. It is due to the internal resistances and capacitances of the wire, which are distributed in nature, where you cannot access those resistance and capacitances physically. Remember. Now, guys, how to find out the resistance of the wire? See, guys, here the resistance of the wire, that you can consider it as like the resistance is royal by A. We can find out those resistances, the internal resistances. Whereas coming to the capacitances, there are three types of capacitances, guys: fringing capacitance, area capacitance, and coupling capacitance. These capacitances plays an important role, especially in metal layers, because in our physical design we follow apartment like a culture. That means within a very less area, we take ground floor, first floor, second floor, third floor, like that, so that you don't require much area within less some square feet only. For example, some around 2500 square feet, you can build some 8 to some 5 to 8 floors. In the same way here also, all our oxidation, photolithographies, doping concentrations and all present in the base layer, and upon them, I mean to say in the first floor, all these metals and diffusions and implantations pins might present in metal layer 1, and afterwards we take metal layer 2, metal layer 3, metal layer 4 and all for interconnections and all. And I'll show you how they are. You see, guys, right side you can see metal layer 1 is horizontal, metal layer 2 is vertical, metal layer 3 is horizontal, metal layer 4 is vertical. Like that, the metal layers are presented in terms of horizontal, vertical, horizontal, vertical. Why? Why don't you take the left hand side figure, where M1 layer is horizontal, M2 layer is horizontal, M3 layer is horizontal, M4 layer is horizontal? Why don't you take in that way? No, we don't take them. Remember, this is very important. In physical design, the metal layers for the interconnections are in horizontal vertical fashion, HV type. Why? Means you need to know about the capacitances, so that you'll understand the reason behind the horizontal vertical routing. Now let's see capacitances. See guys, there are three types of capacitances. Fringing capacitance. You see guys, there is like you can see the blue color one, the metallic layer. The blue color one is one metal. From the base layer, it might have some height, h, it has some width, length, and thickness. You can see in the right side of the figure, from that interconnect, from that metal to the substrate, to the what we call the base layer, there will be some fringing from that interconnected to the substrate. Because of that fringing, there forms some fringing capacitance. Hence, that capacitance is called fringing capacitance. You know that fringing happens from the right hand side and left hand side. You can see here my just a second. Yeah, you can see here. Hope my cursor is visible, and you can see here also. Here it is there, and here it is there. Because of this fringing, yes, there is some fringing capacitance. C fringing is equals to like double times, 2 into epsilon LT by H. Here, we don't consider regarding the width because this fraction is not irrelevant to us, because either this or this means length into thickness. This one, guys. This is fringing capacitance. And we have area capacitance as well. You know, guys, here the area in the sense length into width only. You know, the H also matters. Means what is the distance from the base layer to that metal layer. Because this metal layer could be either, sorry for the background noise, guys. I cannot stop it. I'm sorry. And yes, coming to the point, here this metal layer could be metal layer 2 or metal layer 3 or metal layer 4. It could be any metal layer. If you consider it as metal layer 3, then the height is different. Metal layer 4, it might be different height. So here the height also matters, because as per the equation for the capacitance, area capacitance, it is inversely proportional. Means the upper layer or higher layers have less area capacitance. So the people may ask you why the upper layers are having less area. You can convince them by with this scenario. So that guys, remember, whenever you are going from the base layer to the upper side, or the top metal layers may have less area compared with the bottom layers. Okay. And the last one, guys, the very important thing is coupling capacitance. Coming to that coupling capacitance, guys, here you can see here there are two metal layers. Let's assume it is a metal layer 2 only, which are vertical. For example, they are traveling with the same, what I can say is same overlapping length L dash. Let's assume in the figure the right side metal has a less length, so that the overlap length L dash is present for a particular range only. So whenever there is overlapped length, whenever the signal travels in a particular metal, it might disturbs the other metal layer. Obviously, let's assume you people are staying at some of you might staying at boys hostel, PGs, and your roommate is going for a pub, and in like today's night, let's assume, so that not really some of the people might feel bad or might exaggerate as as your roommate is going for the pub or any late night parties, so that you may disturb for a while. It might be 1 minute, It might be 1 hour, it may be 1 day, but there might be disturbance. But you know, guys, as the physical design taught us, no pain, no gain. Something you want to achieve, something you need to sacrifice. If you want to excel more, you need to sacrifice all your uh, the happy moments also. Yes, I can say from my side, you need to sacrifice s- some of the happiest moments for some period, then only you will achieve. Now, okay, coming to the point. So as the besides one metal wire gets the signal, because of that the other metal layer may gets disturbed, because this overlap length plays key role, which introduces coupling capacitance. As the coupling capacitance is present, there might be some disturbance. It could be in terms of delay, it could be crosstalk, because crosstalk is the basic thing is that only. Because of one disturbance at one metal layer might create some disturbance in the besides metal layer. That's what crosstalk. So here also, here there is some defect because of the coupling capacitance, and that coupling capacitance can be calculated as epsilon L dash T by D, where epsilon is a constant and D is the distance between the two metal layers, and L dash is the overlapped length. Remember, team, the fab guy or the vendor will inform us what could be the maximum overlap length, so that the crosstalk may not happen or it may not disturb the original design functionality. So according to that, we need to work only. Now, coming to the point, you see the two diagrams, guys. You see in the left hand side image, when you take the purple color and the orange color, M1, M2, as the overlapped length is more, there is much amount of coupling capacitance. If there is much amount of coupling capacitance, there might be a delay, there might be a harm because of the crosstalk also. So we don't place the metallic layers in this fashion, horizontal, 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 or vertical, vertical, vertical. We place either horizontal, vertical, horizontal, vertical, or vertical, horizontal, vertical, horizontal, so that the coupling capacitance reduces, so that there may not be harm in terms of delay or in terms of crosstalk, etc. So we conclude that in physical design, the metal layers present in a horizontal, vertical fashion, so that coupling capacitance will be less dominant. That's what the point, guys, regarding the story behind why the layers are present in horizontal vertical fashion. Okay, and this is what, guys, I'll share the slide. I mean, already I shared these slides with our Rajat, and like, please you coordinate with the team so that you'll get it, those slides and all.
Sure.
Yeah, you can say here, just I have mentioned over there, like what is HV routing and why so and all. Everything is cleared, guys, so that the slides may give you some impression in your journey. But remember, guys, you are the driver to your show. You need to drive your show with your efforts and with your hard work. Okay, that's what I want to, like, I want to call off the session for this
Thank you, guys.
weekend.
Thank you, sir. Thank you, sir. Thank you, sir.
Yeah.
Thank you,
If anything, any doubts and all, you can contact Rajat, so that he will forward the same to me, and I'll
You
get
can
back to
ask
you.
now also. If you have any doubt, you can ask now.
Yeah, you can ask now also, team, and I feel comfortable if you ask the doubts and if you interact well.
So one question, when you decide, so in the list of three capacitance, what is the best capacitance? How do we choose that? What capacitance we have to go when we are going for the net lay and this thing,
Yeah.
just to understand the best model out of it.
Okay.
When we choose what?
Yeah. Team, Here the main thing is these capacitances might present in our design. You cannot stop them. So all the three capacitances might present. Coming to our point, here the most disturbing capacitance which disturb us in our journey is none other than coupling capacitance. Because as I said, the metallic layers are like we require metal layers for the interconnections. So the connection could be from metal layer 1 to metal layer 2, from that metal layer 2 to metal layer 3, and again from metal layer 3 to metal layer 2, and then metal layer 1, and then base layer metallic pin. In such journey, the important capacitance among the three is none other than coupling capacitance. The coupling capacitance disturbs a lot. You can ask me like why don't you consider the fringing capacitance and even the area capacitance? See that fringing capacitance, whatever the because of the fringing effect from that particular metal layer to the base layer. Yes, these gets minimized when you go to the upper layers, metal layer 1, 2, 3, 4 and all. So the values generated by the fringing effect, the values generated by the area capacitances and all, they are less dominant. But whereas you take metal layer 1, metal layer 2, metal layer 3, they are not depends upon the height from the substrate to that particular metal layer. They mainly depends on the overlapped length and the distance between the two metal layers. When you go to the higher technologies, you will get some constraints saying that you cannot go beyond this particular distance. You cannot go beyond this overlapped length. In such aspects, we get so many like some what we call some design requirements. According to that, we need to work. In such cases, coupling capacitances um, may disturb us a lot. Hence, we need to concentrate on coupling capacitance. You know, like most of the engineers now, now you are under training. Once you trained and you allot for either in a product company or in a service-based company, you may work on lower technologies. Maybe around 28 nanometer or 7 nanometer. Even some of the people might work on 1 nanometer. But when you come to the lower technologies, there are some special kind of concepts that present only in lower technologies. If you ask me in 180 nanometer or like 45 nanometer and all, those concepts might not present. For example, one of the thing with respect to the coupling capacitance, I can tell double layer patterning that I will show you like once you go a little depth in our physical design. Those are pattern like double pattern layers where there is a restriction saying that you need to uh, go with a particular overlapped length only, a particular distance between the two metal layers only. But I want to take more distance. Then how can it is like how is it possible? That is possible because of the double layer patterning. So that you will see. And coming to your question, team, uh, among all the capacitances, coupling capacitance plays an important role, and that is a crucial in our design. To overcome that, we are considering horizontal vertical kind of environment for the interconnections. Yeah, that's it for that question.
So one more doubt.
Yeah.
What if any step fails in those 8 steps? We should start from the beginning, or like we can do that step.
It depends on the severity of that problem, team. If you ask me if everything goes wrong, you need to start from the RTL team.
Okay.
Suppose if you find there is a mistake at the synthesis stage, till front end all good, it all looks good, then you can start from the synthesis. It depends on the severity. As per your question, if everything goes wrong, then we can start from the scratch. But usually team, some hundreds of people can work. They check double time, triple time, quadruple time. So mostly that the situation might not occur, but because like as I'm in the industry, I didn't hear the such kind of situations. But still, anything can happen. Like we didn't know, we sat nearly some 2 years at home only because of corona. So anything can happen. So I'm telling you, based on the severity of the damage, based on the severity of the cause, it depends. Either you can go from the scratch, or you can start from where the dispute has arrived and all.
Okay, sir. Thank you.
Okay then. Thank you guys. Thank you so much. Thank you, sir.
Yeah, thank you team.
Thank you.
Thank you Rajat.